Hi everyone. In this video, we are going to discuss about the derivation of enthalpy and entropy as a function of temperature and pressure. We can't measure entropy by an experiment, but if I want to calculate enthalpy and entropy changes for a particular system, particular process, then we can measure temperature, pressure. I can call these temperature and pressure measurable quantities. Those can be related to the changes in enthalpy and entropy. In the first equation, I can write that entropy as a function of temperature and pressure. Is it right? Yes, absolutely. This is right. The reasoning for whatever we are going to do, that is for pure fluid, homogeneous fluid, and for any pure system, any pure fluid, single component, the degrees of freedom is 2. So minimum number of variables required are 2. Here I can relate entropy as a function of temperature and pressure. This is right. And if I take the differentiation of this equation, so ds equal to, on RHS, I should write in terms of partial derivative, del S by del T at constant P plus del S by del P at constant T dP. In this equation, I have written entropy as a function of two variables T and P. If I know the value or equation for these two partial derivative in terms of temperature, pressure, or volume, or heat capacity data, then ultimately we will be, our objective will be achieved. Okay, so now let me explain individual partial derivative. Here, let's derive the first thing at constant pressure. What is the value of del S by del T at constant pressure? Okay. We all know the definition of Cp, heat capacity at constant pressure. And I can also write heat capacity at constant volume, that is del Q by del T at constant volume. So these two things are different. Cp, that is the heat capacity at constant pressure. And this is equivalent to del H by del T. This is equivalent to del Q equal to del U, because at constant volume, that will be the relation Q equal to delta U, at constant pressure process Q equal to delta H. Here, and whatever we are going to derive, that is for reversible process. So I should write somewhere reversible process. For any reversible process, I would like to say that del Q equal to TdS. Del Q reversible equal to TdS, and this can be inserted, the del Q here, it can be inserted. So ultimately this equation will become CPT del S by del T at constant pressure, and this will be del S by del T at constant pressure, that is Cp by T. So we have derived del S by del T at constant pressure, that is Cp by T. Okay, that is the one thing. The other thing is del S by del P at constant T. If you refer Maxwell relation, this is equal to minus del V by del T at constant P. This is one of the Maxwell relations. So if I insert these two relations in this equation, then ds would be Cp by T dt minus del V by del T at constant pressure dP. This is the relation of entropy changes in terms of two differential variables, temperature and pressure. Cp, I can measure or I can get the data, I can get the equation, temperature, as well as this is what is the change in volume with a small change in temperature at constant pressure. So this data we can measure experimentally. and this is the equation of ds. Similar equation we can also write for enthalpy. Here also I can expand this equation in terms of temperature and pressure using this type of partial derivatives, but I'm not going to do that because I have fundamental property relation, that is dx equal to TdS plus V dP. This is the one of the fundamental property relations for pure compounds. I can replace this ds using this equation. So if we replace this equation, ds term by this equation, then ultimately dH would be T into Cp by T dt minus T del V by del T at constant pressure and dP plus last term, that is VdP. If I rearrange this equation, this will be cancelled. Cp dt plus V minus T del V by del T at constant pressure dP. This is equation number 2, TH, in terms of two differential variables, temperature and pressure. Now I can use these two equations to solve any problem. If I have a data of temperature, pressure, and this can be obtained from an equation of state. If I know an equation of state, then I can take the derivative with respect to temperature, keeping pressure constant. Cp data will be also available in most of the cases. If Cp data is not available, then I can use the equation, various correlations of Cp as a function of temperature. Those can be inserted and they can calculate. We are going to continue the same problem to calculate delta H in the next video. Thanks for listening.